Okay, so welcome everybody to this session of our Open Innovation webinars. So today the title of the webinar is Fundamentals of Ultrasonic Transducer Design, and the webinar will be given by Thomas Kelley. Thomas has a background in mechanical engineering and transducer design, and he's been with Precision Acoustics for around 10 years. So I will stop sharing now and give the mic basically to Tom. So please, Tom, yeah.
Thank you very much for the introductions, and thank you for inviting me today. It'll be a pleasure to talk to you all. The slides. Okay. So as you probably gathered from the title, in today's talk, we'll be looking at some of the fundamental concepts of ultrasonic transducer design. So as I'm sure you can appreciate, it's a vast topic. So I'm just going to aim to run through some of the basics today, focusing on immersion or contact kind of transducers, just to give you a bit of an idea of the sort of things you'll need to consider when you're looking to choose a transducer for your application, or perhaps if you're looking to design your own sensor. So if you've already got some experience working with or designing transducers, then some of this, or potentially a lot of this, will be familiar to you. But if not, then hopefully it will provide a good foundation on which to begin your journey, and hopefully yield a bit of an insight into the thought process or the mindset to adopt when designing a transducer. Just looking for the next slide now. Okie dokie. What are we going to talk about today in a little more depth? So we'll start with some terminology, naming the various parts of the transducer. We'll cover factors affecting performance, frequency, bandwidth, output, etc. And some of the design parameters you may wish to consider. Then we're going to have a brief look at piezo materials, in particular the piezo polymer PVDF, which is a little bit less well known than piezoceramic. Then we're going to look at the different ways to drive a transducer, the implications of different drive regimes, and how this may affect beam shape. And finally, we're going to run through a couple of case study examples to summarize the design thought process. So, as I just said a minute ago, we're focusing today on immersion or contact type transducers. There are plenty of other types of transducer in existence. So you may have phased arrays, surface wave transducers, bulk clamp designs, so the Longevin or Tom Piltz style for high power applications, CMUTs, EMATs, MEMS, etc. But you know, all of them could fill their own hour-long slots by themselves. So we're going to focus it down today to the immersion or contact style. So these transducers are quite commonly used in industry. So we might be talking flow meters, liquid level sensors, maybe non-destructive testing, that's NDT, that's the acronym. So defect detection, weld inspection, condition monitoring, those sort of applications. You might also get them in medical applications, diagnostic or therapeutic. So perhaps imaging or HIFU, another acronym, high intensity focused ultrasound. Having said that, medical diagnostic applications, they quite often use arrays. I'm not going to talk about arrays too much today, but they are contact transducers typically. So there's a bit of an overlap, as there are with a lot of things in transducer design. So we're going to start with a stylized cross section here through a typical ultrasound transducer. Most transducers you'll come across will incorporate most or all of these features here in various guises. Hopefully some of you are familiar already with this, essentially a textbook drawing, which would be great. But for those of you that aren't, we can label the various parts. So we have the housing, we have the piezo element itself, we have a backing, we have an electrode connection here. So for this particular example, a typical longitudinal wave transducer, the piezo element here has a positive and a negative face, and we must make an electrical connection to either face. So as you can see here, the rear surface connection is made with a soldered wire joint, whilst the front surface connection is made directly through the housing. Of course, this relies on having a housing that's made from something conductive. So if you're going to use something else like a plastic housing, then you're going to need to get an electrical connection to the front some other way. So it could be another soldered connection, or maybe a wraparound tab on the piezo ceramic element if you're using piezo ceramic, and another solder joint that way. So something to think about. And finally, we've got some mechanical and electrical impedance matching in this drawing here. And we're going to go through the functions of all of these parts in some of the slides to follow. So what can we influence with the design? And why bother thinking about the design at all, really? So in summary, we can influence an awful lot with the design. So we can change the frequency, which is the time domain response, bandwidth, the output pressures, power, beam shapes, sensitivity, all of those things. And there are many ways of influencing each of them, and more than just one way of influencing each. So on that note, I guess a really key concept in the sort of design is that all aspects of the design are connected. If you change one aspect of the design, or if you change one of them, some or all of the design, it will influence some, one or all of everything else. So you can't change one thing in isolation. I'd say, in fact, it's such a key concept, everything is linked to everything else, that it probably deserves its own slide. So the first key takeaway is that everything in the electric and acoustic pathway has an effect on performance. I really do mean everything. So, you know, right from the initial drive signal, through all the cables, connections, through the transducer itself, the backing, the piezo, the matching, into the load medium, everything has an effect. And you must consider all of this together to really get the full picture of what your transducer is going to behave like. All right, so starting with frequency, which is a very fundamental parameter of an ultrasound transducer. I'm going to assume we're all familiar with the concept of frequency. So I'm just going to go straight into what can affect the frequency in a transducer. So the frequency is primarily determined by the resonance of the piezo element. But having said that, we can influence it with several other design aspects, which we're going to touch on in a minute. But going back to the resonance of the piezo element, plenty of resonance modes exist. So it might be a thickness mode, radial mode, torsional or a length expander mode. All of these different modes impose geometric or physical restrictions on the size of the piezo. So for megahertz frequencies, which is fairly typical for a lot of contact or immersion transducers, the thickness mode resonance is the most commonly used. It's very effective. So that's the 3-3 mode resonance. That's what we're going to focus on here. So this is where the piezo resonates at a frequency primarily determined by its thickness. So typically the thickness will be half a wavelength or occasionally quarter wavelength in order to get the piezo to resonate. Whether the piezo resonates at a half or a quarter kind of depends on the backing and load impedances and what else you're going to do with the transducer. But most of the time, it will typically work with half wavelength resonance in most scenarios. So this leads us on to some of the design constraints this might impose. So for efficient operation of a transducer in the thickness mode, a good rule to remember is the transducer diameter must be at least 10 times the thickness. Well, that's certainly the case for a typical PZT. So that's an aspect ratio of 10 to 1 in the diameter to the thickness. If you go below this ratio, energy is increasingly given to the other modes in preference to the thickness mode, and the efficiency of the transducer decreases. So this kind of means that thickness mode transducers often use thin disc-shaped piezo elements, as we've got this here. So you can see we've imposed a restriction on the size of the transducer based on the frequency we want to operate at and the resonance mode we want to operate in. So this graph on the bottom right here, you can see this 10 to 1 aspect ratio constraint gives us a minimum recommended diameter as a function of frequency. So 40 millimeters at 500 kilohertz, for example, or 20 millimeters at 1 megahertz for a typical PZT piezoceramic. So this can be quite limiting for some applications, actually. If you don't have much room for your transducer and you need to work with a relatively low frequency, it's very hard to achieve a good efficiency and a good transducer with a small footprint. What can we do? We can play with this a bit. So if we're open to considering other materials with different properties, different effective wave speeds, we could look at a lead metaniobate, for example, which is another very nice ceramic to choose from. Then we only need a 30 millimeter diameter to achieve the same aspect ratio requirement as we did for the PZT, or potentially again a piezo composite element. We only need just less than 15 millimeter diameter at 500 kilohertz to achieve the same sort of aspect ratio efficiencies as we get with the larger PZT. With the piezo composite, there's more at play than just wave speed considerations to allow it to be that small and maintain its efficiency, but we won't go into that today. And of course, there are many other implications of choosing the piezo material besides the thickness and the resonance mode efficiency. Touches on some of them in a bit. So some of the other stuff that can affect the frequency in the transducer, we need to be mindful that the mechanical properties of the transducer can affect the frequency response too. So the type of backing material we apply makes a big difference. So a dense, highly attenuating backing provides quite a significant mass loading. It may drop the frequency in some situations. We might also want to consider the electrode coating on the piezo element. So at higher frequencies in particular, the thickness of the coating can become significant as a function of wavelength and could lead to an effective mass loading in the case of some of the thicker electrode options. So, we might want to consider a thin electrode layer for some of the high frequencies, maybe a sputter deposited layer, for example. In addition, we may get mass loading from soldered joints. So the bottom right, this rainbow colored image, this was a C-scan of an immersion transducer, plain piston transducer with 3 soldered joints on the back of the piezoceramic element. And you can see them very clearly in this near field scan, essentially proxy for surface vibration amplitude. So as you can see, the electrode connections are something you must think about with quite importance as well. So what else? The acoustic impedance matching layer can have its own resonant frequency, which might interact with the resonance of the piezo itself. So this frequency profile for a transducer here, as an example, you can see in this second slight resonance peak here at about 800 kilohertz. This is the effect of adding a matching layer to a transducer which had a nominal 1 megahertz piezo element, but we've also introduced this additional resonance by tuning an impedance matching layer to resonate at this frequency. So we've broadbanded the transducer a little bit through the use of the impedance matching layer. And we'll talk more about them a little bit later. So similarly, the electrical properties of a transducer can affect the frequency. Electrical impedance and matching networks can be used to promote or discard particular frequencies. And we'll come on to that a little bit more later as well. In the case of piezopolymer transducers, the piezo element is very affected by an inherent capacitance, which is a function of surface area, and can lead to the frequency being affected by the transducer's size very greatly. So as you can see up here on this set of graphs, some experimental data for otherwise identical sensors based on one thickness of PVDF film, we could get a center frequency of 5 megahertz with a 25 millimeter diameter, or a 15 to 20 megahertz center frequency with a 10 millimeter diameter. So another consideration, again, is anything else we might want to put in front of the transducer. So maybe this might be a delay line or an acoustic lens. Both of these will affect the frequency. Typically, they'll have a frequency-dependent attenuation, and you might get a downshift in frequency as a result of the lens or the delay line. And the magnitude of the shift will very much depend on the transducer's nominal center frequency and the materials you've used for the lens or the delay line or whatever else you're putting in front of the transducer. So besides the actual transducer design, we've got to think very carefully about the drive signal as well that we're going to intend to use. So if you drive a 1 megahertz piezoceramic transducer with a tone burst at 1.2 megahertz, you will get a 1.2 megahertz output. If you drive it with a broadband voltage spike, so an impulse, you'll get a response essentially equivalent to the transducer's impulse response function, typically centered around the resonant frequency of the piezo and all the other parts that go up to make the transducer. Similarly, high voltage impulses which are not sufficiently broadband or might have too much duration to elicit the transducer's designated frequency will yield some unexpected results. So the drive signal is very key as well in considering the design of transducers. So moving back to some terminology, bandwidth is a very commonly used term, but just what do we mean when we refer to it? Just for those of you that aren't familiar. So here we've got two bandwidths, and you can see they relate to the spectral amplitude as a function of frequency, which is one way of considering the relative amplitude or the transducer's output level if you're driving the transducer with a continuous wave, for example, at a frequency in that range. Alternatively, it's a measure of the frequency content produced by the transducer in response to a broadband impulse, which could contain an even distribution of frequency content across the entire range. So we refer to this transducer here as having an 11% bandwidth. So we look at the upper and lower frequencies, which correspond to the half amplitude point, and we'll compare this range as a percentage of the peak or the center frequency. And there are many, many different ways to quote bandwidth. So if you're quoting bandwidth, it's always best to specify which one you're quoting here. So similarly, this transducer here has a 94% bandwidth. And you might notice that the relative amplitudes of the narrowband and the broadband transducers here, but that is no accident. Leads us on to another key concept, which is the gain bandwidth product. So this is the idea that a transducer's gain or output amplitude is linked to the bandwidth over which the transducer performs. So in a very brief summary, typically transducers with a high bandwidth will typically produce a lower output than transducers with low bandwidth. So high gain, low bandwidth, or high bandwidth, low gain. You can almost approximate it as gain times bandwidth is a bit of a constant. Obviously, there are things you can do to swing it around a bit, but as a general concept, that holds very well. So that leads us on to damping within a transducer. So bandwidth has implications for pulse shape as well as frequency content. So we've got a slide here which has examples, the impulse response of two different transducers. So the top trace or the A scan, if you prefer, is a good example of the impulse response of a narrowband transducer. So it's a high amplitude relatively, and it lasts for many cycles. So it's not great if you're looking to resolve an echo from two sides of a thin sheet of metal, for example, but it's ideal if you're looking to generate a high amplitude wave with enough energy to interact with something, maybe a therapeutic medical device or a high power ultrasonic welding or a cleaning transducer. Perhaps not strictly immersion or contact, but they still very much benefit from low levels of damping, highly resonant structures. So in contrast, this bottom trace here shows a much shorter impulse response, which corresponds to the higher bandwidth. So this would be great for imaging, time of flight resolution, but probably not that great for a high-powered application. So moving on now a little bit to different piezo materials. We've already said that the recommended transducer size can be affected by the choice of piezo material, but we can also influence plenty of other parameters. So I know we've got some piezoceramic experts in the audience today, and hosting it as well here. So I'm not going to go into the details about the material science, as I'm sure there are better placed people than myself to talk about this, but I'll leave you with the takeaway fact that there are different piezoceramic material formulations, and they each lend themselves to particular applications. So whether we choose a hard or a soft ceramic, or a piezo composite, or even a piezo polymer, it's a big decision in the design of a transducer, and we need to consider the end application for the transducer when we're thinking about which piezo material to pick. So having brushed past piezoceramics fairly swiftly, I will talk a little bit about piezopolymers, as they're a little bit less well known in comparison to piezoceramics. So we're going to talk particularly about the piezopolymer PVDF, or one of its copolymers there next to it. So it's typically a thin, flexible polymer film, which can be made to exhibit piezoelectric properties. So we can use it in piezoelectric ultrasound transducers. It's great for use as a receiver of ultrasound, or potentially in pulse echo setups where you're both transmitting and receiving on the same device. It's got excellent G coefficients, piezo G coefficients, but it's not great at producing high levels of power or high amplitude outputs. So it's not a good choice for high power ultrasonics or for transmit only applications. So it's got internally, it's got a semi-crystalline, semi-amorphous polymer structure, which gives it very high levels of internal damping. So unlike some of the more sort of resonant ceramic materials, PVDF very, very readily produces very short pulses, like this one down here in the corner. So it's really great for high resolution imaging applications and that sort of thing. In fact, it's what we base our needle and membrane hydrophone range around, and it gives us the capability to produce sensors with extremely flat, wide bandwidths, which is ideal when you're looking to measure signals containing a wide range of frequencies, amongst other things. So one of the drawbacks of PVDF is its temperature stability. Unlike some piezoceramics, which can operate at several hundred degrees C, PVDF is best kept for room temperature use, or at least probably below 50 or 60 degrees. After this, it begins to rapidly depolarize, as you can see here. And by about 120 degrees, we've found it to be pretty much completely depolarized and no longer effectively piezoelectric. So it's not much use up there at all. If you want a little bit more temperature stability, you could consider one of the copolymers of PVDF. They can offer slightly improved piezoelectric performance as well as the temperature stability, but it's still a polymer. You're not going to go anywhere near as high as you could with a ceramic. And to put it into context, by about 200 degrees, it's melted. So there's really is an upper limit to what you can do with it. So another aspect of transducer design, the backing. So we're going to talk a little bit about backing materials here. Key part of the design. So the transducer backing provides mechanical support for the piezo element and also acoustic damping. So some piezo elements, as we saw earlier, can be fairly thin, particularly at high frequencies. So for high frequency transducers, mechanical support is particularly advantageous. So with our choice of backing material, we can influence bandwidth and frequency to a smaller extent. But we also need to consider what happens to acoustic energy radiating into the backing material. Because a piezo element, it doesn't just radiate forward in the direction we want it to. You need to remember that it also radiates backwards into the backing. So if we don't select a backing material that can attenuate or absorb the energy, then this extra energy will resonate in the backing, and it can interfere with the signals we're trying to produce. So it can resonate in the backing and end up going in the forwards direction, which you may think you could use to your advantage, but typically it's very difficult to control, and any energy going into the backing, you typically want to stay in the backing and never come back out. So we need to consider the acoustic properties of the backing as well as the mechanical properties very carefully. So this graph on the top right, you can see here 3 examples of materials with different levels of attenuation, as we've measured here. And of course, it's very frequency dependent. So you've got to consider the frequency you're working at as well as the material you're thinking of using. So we've got a metal here, copper, which is relatively low attenuation, certainly in comparison with an epoxy resin. But then the epoxy resin itself can be made more highly attenuating by the addition of fillers. And they all pale kind of into insignificance in comparison to the macro composite, which is the yellow trace on the graph here, and is actually the material in the photo here. So this has a vastly improved performance compared to even the filled epoxy, at least over the frequency range it's been designed for. So any energy going into this one pretty much doesn't come back out. All right, so Another concept we briefly mentioned earlier, impedance matching. So in a very brief summary, the performance of a transducer can be improved by adding a layer of intermediate acoustic impedance, or even multiple intermediate layers between the piezo element and the load, ideally at a quarter of a wavelength thick. So for anyone unfamiliar with the concept of acoustic impedance, it's the product of the material's density and the wave speed. It's got its origins in transmission line theory, where at any boundary between dissimilar impedances, you will get a transmission and a reflection of the incident energy. The relative levels of the transmission or reflection will very much depend on the acoustic impedance of the two media, as per the formula here. So there are various theories on the best impedance to use for an impedance matching layer to aid transmission across the boundary and essentially smooth out the impedance difference. But as a guide for a single impedance matching layer, you could be targeting an impedance that's about the geometric mean of the product of the square root of the product of the two impedances between piezo and the load, as written here. So material science plays a fairly key role in the choice of matching layer. Obviously, you need to have an impedance close to the target impedance as possible, but you'll also need to consider how you're actually going to achieve the fabrication of it. So to put it into context, the wave speed, ultrasonic wave speed in water is maybe 1480 meters a second, depending on temperature, etc. So at 1 megahertz, we're looking at just under 1.5 millimeters. So quarter wavelength would be 375 microns, or at 10 megahertz, quarter wavelength, 37.5 microns. So to produce quarter wavelength layers, they become very thin, and we must consider how we're actually going to achieve them. In practice, we'll need to consider the wave speed in the matching layer material itself rather than water, which is likely to be the load. So it may be faster, in which case we could use a thicker layer, but we're still looking at very thin layers, and we still need the ability to tune them very accurately. So as we saw earlier, we can influence the transducer's bandwidth with the use of matching layers. If we specifically target a slightly different frequency to the natural resonance of the piezo, we can encourage the transducer to resonate at the new frequency, and we've effectively gained some bandwidth or a resonance that we didn't have before. So they can be quite a key tool. So in the same way as mechanical impedance, acoustic impedance, we can now consider electrical impedance. So in the same way as energy is reflected at a boundary in acoustic impedance, energy is also reflected at boundaries of electrical impedance. So if you're driving your transducer from a 50 ohm source, which is pretty typical in many industries, then in order to get good power transfer to the transducer, you should match the electrical impedance of the transducer to that of the drive circuit. So electrical impedance is usually measured as a complex number, the sum of resistance and reactance here. The reactance is capacitive or inductive and is very much frequency dependent, although resistance is also frequency dependent in the context of RF. So electrical impedance matching, typically transducer assembly, so a piezo element or a piezo element with a backing and a matching layer will not naturally be a good impedance match to your drive circuitry. Sometimes you can get lucky, or if you're designing a drive circuit around your transducer, then you can accommodate whatever impedance you've got, but quite often you'll need to tune the electrical impedance of your transducer. To that end, you can perform electrical impedance matching using passive components, inductors or capacitors, to correct for any reactance in the transducer, or you could use transformers to adjust the resistance in addition to any passive components. So being a frequency dependent property, the impedance cannot be tuned to a perfect match at all frequencies at any one time. And that's a key point to remember. As you can see here on these little Smith chart pictures, which are normalized to a 50 ohm central point, we can choose from a narrowband match where we have a single frequency selected to be matched to 50 ohms exactly, at the expense of all the other frequencies, which are quite a long way from 50 ohms. Or we could choose a broadband match where there's no single one frequency at 50 ohms, but there's a really wide range of frequencies that are kind of equidistant to 50 ohms. So the kind of electrical match you may wish to perform, again, will depend on your application. So at this stage, while we're considering the electrical side of transducer design, we should also consider cabling. The choice of cable can have a vast impact on transducer performance. And if possible, and it's very much a preference, a cable with a controlled impedance should be used. So very commonly a coaxial cable, 50 or 75 ohms very commonly, or perhaps a twisted pair with very much more ability to tune impedance, but the twisting needs to be carefully controlled. Or perhaps a microstrip or some strip line if you're designing transducers on circuit boards. So moving on to drive circuitry, how we drive transducers. What we're aiming to achieve with the transducer determines how we should drive it. And how we will be driving the transducer provides input into how we'll design it. So if we're looking for high pressure or power outputs, we're best driving the transducer with a sine wave input. The sine wave allows the transducer to ring up, reach its full resonant steady state. Sometimes this may require a couple of cycles to achieve, or sometimes it may require 5 to 10. It really depends on the design. You can see this portion of the waveform here is the ring up. We reach the steady state, and then when the drive signal is shut off, we get the ring down as the remaining energy leaves the device. So if we're looking for a short pulse for a time of flight measurement, then we probably wouldn't consider driving it this way. We'd may consider driving with an impulse to minimize the pulse duration. So the pulse over here on the left, for example, is the impulse response of a broadband transducer. And you can see that the entire pulse is over within 200 nanoseconds. We could achieve a similar, but perhaps not quite as short pulse if we drove with a single cycle of a sine wave input from an amplifier and a function generator combination. But if you're only ever going to use short pulses, then the size and expense of an amplifier that's capable of supplying significant power might be quite unnecessary. So in summary, whilst you might be able to drive a transducer in several ways, it's definitely worth considering what you actually require so you can optimize the efficiency of the drive circuitry as well. So back to a little bit of terminology, this time beam shape. So very quickly, we typically define the acoustic axis in the axial direction, which is the main direction of propagation from a transducer, and the transverse directions are orthogonal to this. So sometimes this might be the X or the Y axes. So considering all that, if we start looking at an axial beam pattern, here we have a simulation of a field produced by a planar transducer operating in a continuous mode. As you can see, it's quite a complicated field shape, particularly in the near field close to the transducer. And although it's a planar transducer, it's still got minima and maxima on and off axis. So the complicated looking portion of the field near the transducer, that's the near field. In this region, the transducer's field is indeed quite complex. Both the axial and the transverse profiles are not necessarily smoothly varying. So the last axial maximum here is also considered as the end of the near field and the beginning of the far field. In the far field, the beam shape is much more well defined in all axes. The position of the last axial maximum, sometimes known as the natural focus, is set by the size and the frequency of the transducer. So with A being the radius up here and lambda the wavelength, you could also consider it as the longest focal length achievable for a particular combination of frequency and diameter, as it's essentially the focal length of a planar transducer. So if we now look at a simulation of a similar planar transducer, but driven with a single cycle of a sine wave, you can see how the on-axis amplitude compares with the previous continuous wave example. To note how the on-axis maxima and minima are very much reduced, almost completely. So there's not really the same near field, far field distinction. This is related to the interaction or lack of interaction between the main plate wave and the diffracted waves from the edge of the transducer. But in summary, you can influence the field shape by your choice of drive regime. So that's the takeaway when considering designing a transducer here. Other tools we have, a particularly important tool, the concept of focusing. We can focus the energy radiating from a transducer by either curving the radiating element or applying an acoustic lens, as we briefly alluded to earlier. There are other ways we could manipulate the beam, maybe a phased array or some electrode apodization, but the general context of a focused transducer is the same. So with a focused transducer, we can concentrate the energy into a smaller area. It may have benefits increasing the energy density or the intensity, particularly in the case of HIFU treatments. Or it might be good for improving resolution for defect detection in industrial applications. So on to transducer directionality or directivity. So this is a function of frequency and geometry. So for a fixed frequency, we can change the directivity by varying the diameter of the transducer. There are various models which can be used to predict directivity. So the rigid baffle model for a circular plane piston shown here. And you can see it's affected by the wave number K and the radius of the transducer A. So as it says here in summary, for a fixed frequency, a smaller transducer will have a wider beam spread. Although if you consider the beam width close to the transducer, a wider transducer will have a wider beam width, but not necessarily the spread. So there are definitely beam shape implications when choosing a transducer geometry. If you want to play around with asymmetric beam patterns, for example, fields which are very divergent in one axis, but less so in another, you could consider non-circular radiators, rectangular geometries, where the piezo is longer in one axis than the other, and that will lead to that sort of behavior, which can be a useful tool for some applications. So the same applies to receivers, or hydrophones, as they're known in immersion use. You can see some data here on the directivity of two different sizes of needle hydrophone. So this is for a fixed size and varying frequency. You can see that the smaller hydrophone is far more directional than its larger counterpart. So jumping back to the near field, far field considerations that we touched on a second ago, we've got a few examples here of some transverse beam profiles in both the near and the far fields. The aim of this slide is to demonstrate just how much the field shape can vary within the near field. So considering a transducer driven in a continuous wave mode, these two profiles on the left are taken only 1 millimeter apart axially. And you can see that in the first one, we have an on-axis minimum, while in the second, we have an on-axis maximum. Such is the rate of change of the field in the near field. In comparison, the far field is much more conventional and obeys the usual sort of formula for a central main lobe with symmetrical side lobes of decreasing amplitude, as you see in a lot of the books. So a very brief bit about measuring acoustic fields. Having talked about radiation patterns, it's probably worth mentioning a few considerations for hydrophones used for measuring fields. So again, the measurement of acoustic fields is a topic that could fill its own hour-long slot, but merely introducing the concept here, pressure fields can be measured with a hydrophone. So these devices, which we've got a couple pictured here, as we saw earlier, some needle hydrophones and a membrane hydrophone, they will typically produce a voltage in response to a pressure stimulus. And with proper calibration, the voltage reading can be converted into a pressure. Hydrophones, as we saw a minute ago, they also conform to the physics of directivity, so they must be carefully aligned with respect to the acoustic field before making measurements. And an additional consideration in selecting a hydrophone is the size of the hydrophone. Well, the size of the hydrophone itself, but in particular the size of the sensing element. If you're looking to measure fields in the megahertz frequency range, for example, where wavelength in water is in the millimeter or sub-millimeter range, then you're going to be missing a lot of features and generating some large spatial averaging artifacts if you use a hydrophone with a sensing element that's not sub-millimeter. So sensitivity is another key consideration. You must use a hydrophone with sufficient sensitivity to detect the signal you're trying to measure. If you're using a hydrophone with a sensitivity, for example, 100 millivolts per megapascal, and the signal you're measuring is only a kilopascal, then you're only going to generate 0.1 of a millivolt from your hydrophone. So if your acquisition, if your oscilloscope has a 1 millivolt resolution, you won't be able to see the signal at all. So it's not hydrophones are not a one-size-fits-all. Choose them very carefully in context with the transducer as well. All right, so finally, I think it's worth mentioning some environmental considerations. It might sound quite obvious, and it probably is to a lot of people, but these should really feature quite early on in the design process when considering the application, as all the design choices can be impacted by restrictions imposed by the eventual operating conditions, whether it's high temperature environments or the transducers going somewhere where there are corrosive, damaging substances, or high pressures or high radiation environments. All right, so we're going to end up finishing the presentation with a couple of examples of the design thought process. So we're going to take one from an industrial setting, looking at some small defects in a metal plate. So the first thing we would probably do is look to define the problem that we're trying to solve. So the first questions we may want to ask ourselves when thinking about transducer design are maybe how small are these defects? Where are they located? Specifically, perhaps how far from the surface, or maybe how far from any surface? If we know how small the defects are, then we can make an estimate for the beam width we need. in order to see them clearly. We can also get an idea for the frequency we need to achieve this. So how far from the surface tells us what sort of axial resolution we may need, or temporal resolution. So this pulse here, for example, it's the same as the one earlier. It's only 200 nanoseconds long, but in steel, that equates to about 1.2 millimeters at 5,900 meters a second. So a pulse duration any longer than about 200 nanoseconds is going to make it very difficult, without some signal processing, to resolve defects that are about a millimeter apart or closer. And a pulse length of this duration is going to lead us to a frequency of about 10 megahertz or higher, and it is a very broadband pulse. So we'll also have to think about the amplitude of the signal and how we're going to drive the transducer. So going on to the solution, the application clearly requires a high bandwidth to achieve the short pulse. It needs a high frequency to keep the beam width narrow and to keep the pulse duration short. And it needs a narrow beam width if it's to be capable of resolving the small defects accurately. So the solution could be, it's not necessarily just one solution, but the solution could be a focused transducer at 10 megahertz, say. It could be made from a piezopolymer film, or maybe a broadband piezoceramic, a lead metaniobate or something. PVDF would be all right, as we're assuming it's going to be a room temperature environment. Maybe we're working pulse echo, and that's all right for PVDF, as it's pretty reasonable pulse echo, and it's got good receive capability. So there might still be some compromises to be made. There's, I guess, another key takeaway of the transducer design process thinking is there are almost always compromises to be made. The higher the frequency we choose, the more attenuation there will be in the metal. So any signal returning from a defect would be smaller. We could put the drive voltage up to compensate maybe, but the temporal duration of the impulses tends to increase with amplitude. So it's likely that any acoustic pulse would become longer, and we may not be able to resolve things as close to the surface of the metal, perhaps. So if we want to increase the range, we may need to lower the frequency and sacrifice some of the lateral and near surface resolution. We might also have to compromise between the lateral and the axial resolution, and that may affect our choice of focal length. So there appears to be a solution, although, as is almost always the case, there will be some compromises. So one final example from a different sort of industry, perhaps a tissue heating experiment of some sort. Again, we ought to start by defining the problem. So what area or volume needs to be heated and by how much? Clearly, we're going to need a high power transducer, but the question is, how powerful does it need to be? We could work out total power requirement by starting from the temperature rise we want to achieve, using information on heat capacity of the tissue medium, the focal volume of the transducer, make some estimates for the energy needed to induce the required thermal rise, assuming all or most of the heating occurs in the focal region. We could convert the energy figure into a power figure by considering a duration for the intonation. And of course, there are a few very large assumptions there, as absorption levels or attenuation within the target medium. But that sort of thinking along those lines gets us to a place that's close enough to begin thinking about transducer parameters. Really, for this sort of thing, there's some good benefits to be had with some FE modeling if it's a particularly complicated scenario. But that sort of process, that sort of thought process outlined here gets us going. So as a solution this time, maybe we'll go for a hard piezoceramic transducer capable of outputting decent power levels. Again, focusing would be pretty beneficial for us. in that it will increase our ultrasonic intensity and localize the heating as we required in the scenario. We need to drive the transducer with a high power input, so we'll likely need some form of amplifier. And in this case, electrical impedance matching becomes quite critical to avoid excessive energy losses in our system and to ensure that the transducer can actually deliver the required power. So I guess as a final summary of the design process, a couple of questions that you should probably ask yourself, beginning with considering what you actually want to achieve with the transducer. A very key question. Then sort of moving on to considering what do I need to be able to achieve this? The bandwidth, output, the pulse length, the beam width, the drive side. And it's worth thinking about what you can compromise and what you can't compromise on. Because as we said, a lot of applications will require compromise somewhere. So it's really good in establishing in your own mind which parameters you're willing to compromise and which can't be compromised. And going to put one of the previous key takeaways in there again at the end, that everything is linked. You can't change something without affecting something else. That's definitely one not to forget when thinking about transducer design. You can't change something without affecting something else. So I think that pretty much leads us to the end today. There's a few additional resources. If you like the sound of what you heard here, a few additional resources and some tutorials from one of my colleagues on our website. So they're all free to access. I can highly recommend them. And that's the end. That's everything from me.
Okay, thank you very much, Thomas, for this really nice overview. I think a very clear presentation of the many trade-offs that need to be made. I hope you will stick around if there are any questions. I can say that we have one on the chat already from Abdul Kadir Abdi. So he's asking, are the aspect ratios the same for different thicknesses? So I'm not sure if you are quite clear on which case he refers to. Do you understand what means? Yeah.
Possibly not. So are the aspect ratios the same for different thicknesses? So I guess being a ratio, the aspect ratio itself is regardless of thickness. So you take the thickness, you apply the ratio to it, whatever the thickness is, apply the 10:1 ratio or whatever the ratio, and you end up then with the diameter. So I guess the answer is it is regardless of thickness, as a general rule.
Yeah, it's possible that he was referring to a specific slide, but I'm not sure about that. Maybe if he has further questions.
Yes. You're always welcome to get in touch if anyone has further questions or any questions that you think of subsequently.
Yeah. Can I? There's one more question that we can move on to. I think from Mohammed Afifi Mahmoud. So he's saying, thanks for the talk. And how can we operate a phased array with many single elements for imaging applications?
How can you operate a phased array of many single elements for imaging applications? I guess it very much depends on how many elements you're looking to operate. I guess the key there is how to drive them. So you'll need well, typically phased arrays will be used with a phased array controller or a phased array drive unit, which will have some focal laws programmed into it for various focal lengths, various element geometries. But if you're starting from scratch doing it yourself, then it's quite a lot of work. You need to do a lot of the focal laws yourself. And but if we had a low element count, for example, if it was only sort of 4 or 8 elements, then it's a little impractical, but it's still within the realms of possibility for acquiring 4 or 8 discrete laboratory amplifiers and sending the signal to each of them and controlling the inputs to the amplifiers through some sort of software means. But if you're looking at high element count arrays, then that approach becomes a lot more impractical. If that helps to answer the question.
Yeah, I think it helps, and maybe we can add that there are also some integrated circuits that are meant specifically for driving multi elements. But I think it's probably going a little far. But
Yeah,
the audience is at least invited to look at integrated circuits for this. Do you have comments for this?
No, I think that's a very sensible suggestion. Maybe the final point is that an array of single element transducers put together is probably no different to an actual phased array that's built as a phased array unit. I'd expect you could drive it in exactly the same way as you would a regular phased array probe, as long as you're conscious of the element geometry and the relative spacings.
Yeah, good. We also, I think we also have a question on the chat from Sayed Musavi. He's saying learning about designing ultrasonic transducers is very difficult. Can you introduce a good reference to start with? So I think maybe an article or a book. Do you have any particular ones, Tom, that you could?
That's a very good question. I don't think I have a favorite book or reference that summarizes the transducer design process succinctly and completely. So I probably can't advise on that, I'm afraid. I know there are many research papers, white papers, and published papers out there that detail various transducer designs. A lot of them, maybe they're not going in for the fundamentals. Maybe they're sort of starting with a pre-assumed level of knowledge and focusing on a specific aspect. But I think you can learn an awful lot from of transducer design from reading the sort of research papers that are out there, and it may be tailored towards the topic you're looking to investigate.
Okay, thanks a lot. So I was maybe I have a quick question myself. So I think some might be a little surprised about one of the initial examples you gave, that for example this PVDF film of, I think, of 9 micrometer, how the diameter was affecting the frequency. Of course the thickness would clearly be affecting it, but the influence of diameter, I think, through capacitance. Can you elaborate a little bit on this?
Yes, I guess so. You could consider the capacitance of a transducer element to be that of a parallel plate capacitor. So E naught A over D, with A being the area and D the thickness. So piezoceramic elements obviously have an inherent capacitance, but the capacitance in PVDF film is very much greater. It's very much owing to the thinness of the PVDF film. So we were looking there at the film thickness of 9 microns. So if you consider that into the order of the parallel plate capacitor, you have an incredibly high capacitance, and it's in your circuit. There's no, it's inherent. You can compensate for it, but you can't take it out, and it weighs very heavily on the frequency of the transducer that you build with the film. As we said, the PVDF is not a resonant structure in the same way as other ceramic materials. So whilst the frequency is affected by the thickness and there is a bit of a resonance, it's very much less well defined than for a lot of the more resonant materials, if that helps.
Yeah, I think so. So yeah, of course, it's clear how you have the influence on capacitance through the diameter, but as you're saying, it really behaves in a special way. This PVDF film, and then as you're saying, the capacitance really affects the whole mode of operation, basically. Yeah.
Yeah, and you can look at the different films. You can look at thicker films and do the same comparison with diameter. And the thicker the film gets, the less it is affected by the capacitance, or the less the frequency shifts as a function of area. Purely,
Okay.
it's the thicker film with the lower capacitance.
Okay. Thank you very much for also answers to these questions. So I think we will say thank you now, and the audience is also encouraged to look at some of the resources that you showed on the website. I think that there's a lot of information to be found there. So thank you, and I think I'll just share the screen again from here, just to point out that the next talk will be in 2 weeks, and it will be done by Thomas Savara from the company Ultrasonic in Denmark, and the topic will be high intensity focused ultrasound. So yeah, Dr. Savara has a lot of experience on this from the company specialized in this. So please, if you haven't registered already, you should consider it, and you can find the registration link in the same way as you found this one. So before we end, let me just encourage everybody to do the evaluation. So please take a little time to give us some feedback so that we can improve these webinars, and you may comment on this one specifically, and also on the choice of topics that we have. So please help us by doing that. And with this, let me say thanks to everybody, and hope to see you in 2 weeks.